Good morning, sir. I am Vikrant Mishra, convener of this event. And I can't express my gratitude that you have joined this function and you are gracing this function with your eminence presence.
Thank you very much indeed. I'm honored to present here. It's a pleasure.
So, thank you. Welcome back, all the participants. Dear participants, welcome back. In this, so once again, welcome all the participants in this International Conference on Materials, Manufacturing and Energy, organized by Department of Mechanical Engineering, Rajki Engineering College, Manpuri, Uttar Pradesh, India. And we are back here with more enthusiasm and to gain wisdom, and as we are pertaining the opportunity to be between such knowledgeable personality. Now, very fortunately, we have a splendid presence of our next keynote speaker, Professor Brian Norton, DIT President, Dublin Energy Lab, Ireland. Professor Norton's interdisciplinary research is on understanding how to harness diverse interlinked characteristics on both solar energy and our natural and built environments to reduce greenhouse gases emissions associated with energy use. Professor Norton's work has been influential in policy advice on reducing greenhouse gas emissions, marking the publication of an influential major report on decarbonization of buildings in Europe. Sir is currently Vice President of the European Sustainable Energy Innovation Alliance and the Daylight Academy Steering Committee. As part of putting his expertise into practice as President of Dublin Institute of Technology, Professor Norton had realization of 70-hectare campus as an integrated, environmentally sustainable addition to the city. His work has been recognized by numerous awards internationally. This include in the UK, the Honorary Fellowship of the Chartered Institute of Building Services Engineers, and in Australia, being formally recognized as Solar Energy Pioneer at the 50th Anniversary Solar World Congress of the International Solar Energy Society. In Ireland, he is a member of the Royal Irish Academy and the Irish Academy of Engineering. Sir has received an honorary doctorate from the University of Technology in Troyes, France. Sir is currently Head of Energy Research, Tyndall National Institute, Research Professor, UCC, and Professor of Solar Energy Applications at TU Dublin. Sir is the Principal Investigator at MAREI and Irish National Center of Energy, Climate and Marine. He is Secretary of Policy and International in Royal Irish Academy. So now we cannot wait to hear him. Sir, I request you to kindly enlighten us with your precious words. Welcome, sir.
Thank you very much indeed. It's a pleasure indeed to speak. It would be nice to be in India, but still nice to talk to you all online. If I can share the screen here, let me just get my let me just share the screen. Can you see my screen is my first question.
Yes, sir. Yes, sir.
Excellent. And you can see, and if I just do this, can you now see the slides? Can you see the slides okay?
Yes, sir. It's okay.
Brilliant. Excellent. Excellent. Okay. What I'm going to talk about is the decarbonization of buildings. And I work, as has just said in the very kind introduction, in Ireland, in Europe, and my examples of some of the statistics are European, although I try to give them some Indian context as we're going through. But the challenges I'm going to discuss are actually universal. They manifest themselves in different ways in different places, but they're actually quite universal. One of the key aspects of that, of course, is that when you're looking at buildings, they're very dependent on how they're occupied, the type of buildings, and the climate. So although some of the challenges are general, the solutions are very locally specific. As was said, I'm head of energy research at Tyndall National Institute in Ireland. Part of that is the International Energy Research Centre, the IERC, which is on the logo there. MARI is the National Centre for Energy, Climate and Marine. I'm one of the PIs there, and Professional Solar Energy Applications at TU Dublin, which are my affiliations. So if we why is decarbonisation of buildings important? Well, if you look at the European numbers, buildings produce about 25% of total European greenhouse gas emissions. About 2/3 of those emissions come from residential buildings, about 1/3 from non-residential buildings, and a lot of that is due to space heating, and a lot of that is a lot of that energy is fundamentally fossil fuels and produces CO2, and is one of the drivers for greenhouse gas emissions and climate change. So to mitigate climate change, one is seeking to replace the fossil fuel use with renewable energy in buildings, and more fundamentally, reduce the energy use in buildings altogether. So that's the big picture, and these are some European numbers on that. So essentially the key idea in this is that the graph you see in the middle there, you see there's a target with an arrow in it, okay, and that target is where you want to get. And to do that, you need to do 2 things: reduce the energy use over time. So you see a line that's reducing over time, and then the energy use that remains, having reduced it, one's seeking to meet with decarbonized electricity and heat. In other words, electricity and heat that are coming from renewable energy sources. So there are 2 things one needs to do. As the equation at the bottom, decarbonization of buildings is reducing the energy demand from building, and it is increasing the supply of that reduced demand from renewable energy sources. And part of that, as you see from the graph on the right, is building standards. The standards of thermal insulation, of air tightness, of efficiency of electrical appliances, etc., have increased over time. Okay, and for new buildings, those increased standards have reduced energy use. So essentially, if you again look at new buildings, this leads you to the concept of a net zero energy building. And essentially what that means is that you normally have traditional building, which is in red on the figure in the middle there, and you seek to reduce that. So at certain times of the day, at certain times of the year, the building is actually producing energy. So it produces energy from PV, from solar thermal, from devices that are on the building, okay? And that's either self-consumed within the building, or is supplied, for example, electricity from a PV array on the roof, supplied to the grid. And the net effect means that in balance, the building has net zero energy consumption. It has energy consumption, but it produces as much energy as it consumes, okay? And you get this idea of a net zero energy building. And that is very good for new buildings, and you can see a whole range of little photographs of different types here. I show those photographs to show that although the concept is common to all these buildings, the architectural realization of those buildings is quite different. And so in a way, a net zero energy building can look like anything. There's no particular building style or aesthetic function, for example, that comes out of that descriptor. So it can look like a whole range of buildings. But the key thing is that one's seeking to have a net zero energy consumption, and that is readily achievable in nearly all climates for new buildings. One of the interesting things, however, around this is that when you look at net zero energy NZ buildings, it's often seen as a goal, but it's calculated in terms of primary energy. In other words, the energy generated at the power station. And so the the net zero energy depends to a certain extent on the losses, transmission losses and combustion losses, etc., at the power generation system. Now that obviously decreases as the conversion losses decrease as well, but because of the way that is calculated in most calculations, the net zero energy building is actually meaningless to most homeowners. What they are concerned about is actually the figures on the left of this, which is actually the energy that's delivered to the building, how it's used, and what energy is needed, and so it's important we're looking at these things to make sure that one's looking at net zero energy building from an occupant's viewpoint, not necessarily from the power system viewpoint. And if you allow, for example, the primary energy calculation and simply replace that primary energy with PV, it means that you actually incentivize not improving the energy performance of the building, because you've now got a net zero energy building because it simply generates lots of electricity for photovoltaics, but it can still be an energy inefficient building in itself. So the important thing to think about when thinking about net zero energy buildings is achieving a net zero energy building with the balance of both energy efficiency and the idea of primary energy as well. So this applies, all that I just said applies to new buildings, but actually new buildings are in all countries are very much the minority. This figure is countries across Europe, okay? And what these ratings are, I'll show you the buildings that have different energy ratings. The ones in green are the very high rated, very energy efficient buildings at the bottom there, and the ones in various shades of red are very energy inefficient buildings. Those energy inefficient buildings are older buildings. Okay, so the new buildings are essentially the green at the bottom and some of the yellow, and the old buildings are the red. And what this graph shows you is that existing buildings are the majority. That's obvious, and that existing buildings have major problems in terms of their energy efficiency. So although net zero energy buildings can be readily achieved in the context of new construction, the real challenge is how you deal with existing buildings. So again, an example in Europe of how to deal with this. This is an apartment block in Estonia, in Eastern Europe on the Baltic, and you see the building before and you see the building after. Okay, and what has happened to this building? And this is social housing. So the occupants of this building are paying rent to a social landlord who refurbishes the whole building and passes on the benefits of that to the tenants of the building. And this is a building renovation. So what has happened is the fabric has been better insulated. There's been draft proofing. In other words, the air infiltration through the building has been reduced so that the heat losses because of warm air being lost from the building have been reduced. There's actually renewable energy generation on the roof. You can't see it in this picture. There's new windows which have very low heat loss. Okay, and interestingly, you'll see before these balconies. In the final building, they're replaced with additional rooms in the buildings, and that's what's called a volumetric addition. The volume of the occupant space has been increased, so the volume of the occupied space has been increased, and the reason for that is that the energy refurbishment reduces energy costs, okay, but provides few other benefits to the actual occupants of the apartments. And by increasing the volumetric addition as part of the refurbishment, it's giving up a clear benefit and a clear incentive to the tenants to become more energy efficient, well, because they're getting additional space as part of that exercise. So this is typical refurbishment looks like, and this, I say, is in the context of social housing, where one organization owns the whole building and can then do refurbishment at scale in a cost-effective manner. However, if you look at the bottom right-hand side here, this is a thermograph, an infrared picture of a row of houses, and this one in the middle, which is purple, showing lower heat loss, okay, has been refurbished. All the adjacent buildings have not, and this is a problem in that these are buildings that are occupied by are owned by different people. Okay, and so the responsibility for refurbishing the building rest with different people. Okay, this person who's got the one that's in purple in this infrared picture has refurbished this particular building, but the adjacent buildings are not refurbished. Two problems with this. One is obviously all these other buildings are still energy inefficient, but secondly, this doesn't get scale in terms of being able to do refurbishment. So the costs of refurbishment here are much greater, whereas the cost for this apartment block, because there was scale and there was production scale in terms of doing that refurbishment, in terms of sourcing the components, etc., meant that this was much more lower cost. And so the payback for the energy refurbishment in terms of the energy saved was much shorter. Here, because you're doing it in a one-off situation, is going to be much greater. And I'll come back to some of those issues of economics and such like later. This is a calculation I did for a report, and I'll show the paper reference at the end, which looked at the importance of building refurbishment in the bigger picture. Now, I don't have time to go into all the detailed assumptions behind this calculation, but what this essentially does is there is a scheme within Europe called the European Union Renovation Wave, which essentially is refurbishing 3% of existing buildings each year. Okay, and that's represented by the blue dots on this graph. The black dots on this graph represent what would happen if you went as business as usual. BAU. In other words, one didn't do that refurbishment. So, so these are two graphs, and this is time on the lower axis, and this is working through to what this would mean in terms of the overall temperature rise due to greenhouse gas emissions. Okay, so this is relating the greenhouse gas emissions to the temperature rise and relating it to the refurbishment of the stock. So, and it's assuming all other numbers are the same. That's a very big assumption, but just give it a broad calculation. And what's this showing is the forms aiming to get to a 1.5 degree temperature rise. In other words, that's the temperature rise that you find acceptable. Even with the planned refurbishment of buildings in Europe, one still wouldn't achieve that. If one's saying that one's happy to accept a 2 degrees C global Celsius temperature rise, then the EU refurbishment strategy will just about meet that number, but only just. If you do nothing, there's actually no hope of meeting any of those targets. And this shows the importance, it shows the contribution of energy in buildings to overall emissions, which is very, very high, but also shows the importance of refurbishing existing buildings to do the energy refurbishment of existing buildings. Okay. That's a little bit of the context as to why this is important. What I'm now going to go on to discuss is some of the key challenges in doing this, and it's not all of these challenges. We don't have time to discuss them all, but I'll try and give some time after I finish speaking to ask any questions around this on both what I present and also any other related issues, by the way. So I'll try and give time for questions at the end. The first challenge is to do with how you actually know how much energy buildings use. All countries in the world produce statistics that show how much energy is used in their buildings. Yet that is actually, but no country in the world actually measures all the energy use of all the buildings. So, so how do they get to that calculation? What actually is done is buildings are rated, as you saw in the earlier figure I showed, from A to D, where A is your best and D is your worst. Based on that calculation of the rating of the buildings, one ends up with the theoretical rated calculation of energy use in that building, and then you sum up how many buildings there are in a particular jurisdiction. So essentially, how building energy use is calculated at a national level is done theoretically, and there are no actual measurements underpinning it. Now, the problem with that, and this graph on the left here is an example in the Netherlands. This is showing actual energy consumption and showing the theoretical consumption. And this theoretical consumption is the number that policymakers use because it's based on a standard building or standard building type, but this assuming that all buildings essentially are built to the particular building regulation in force at the time of construction, a particular energy use profile, a particular profile of how the buildings are occupied. Okay, so you end up with a theoretical consumption, and these numbers A, B, C at the D, E, F, G at the bottom are the energy ratings. So A is very well-rated building, those new net zero energy buildings I talked about earlier, whereas G and F would be very old buildings with very little, for example, in Europe, thermal insulation would have very lot of air movement, etc. And two things you see. One is that for older buildings, the theoretical consumption is much higher than it actually is in reality. So very significantly, with very significant error bars on those calculations. But for newer buildings, the actual energy consumption is higher than it is in reality. Now, why is that the case? Well, in older buildings, it's assumed that buildings their construction remains the same as the building regulations, the building codes, the building regulatory requirements at the time of construction. But what actually happens is buildings are improved, they're changed, insulation is introduced, windows are replaced, etc. So the actual energy consumption is very much lower than actually anticipated. Buildings don't stay as they're originally constructed. Okay, so that's the explanation for the differences for very poor buildings. For very, very good buildings, a different effect is in place. These buildings are, and here I'll give you a European example, well insulated, they have low air change rate, they're very comfortable, they're very warm. And rather than taking those benefits as energy efficiency, people take them as higher comfort temperatures. In other words, under very cold conditions, because the buildings are very well insulated, etc., they would have them the occupants have the building at a higher temperature than they would have done otherwise. Okay, and that's called a rebound effect. In other words, you're taking the efficiency gain not as energy saving, but as a higher internal temperature, and so your actual consumption is higher. Okay, so you see, so the first thing is that national statistics, which are based on the dark gray bars here, are often wrong. And if you look at it in total, you've got two reference lines, the figure on the right, which show you the upper and lower limits, but real buildings sit between those limits, and where they actually sit, no one actually knows. So the first problem in looking at the improving the performance of existing buildings is no one actually really knows what the actual performance of existing buildings actually is. And there's a need for much more measurement of real building performance rather than just theoretical calculations. The second issue I'm going to talk about in terms of challenges is buildings exist in an energy system. And that is, and as they become more efficient, that's increasingly the case. So that you see here the buildings have the energy consumption in a sense, but also, for example, they have heat storage. They'll have batteries for the PV. Might have a fuel cell in the future. If you've got a photovoltaic on a building, the building's occupant is both a consumer of energy and a producer of energy, a so-called prosumer, and so is actively both providing energy to the system as well as receiving energy to the system. But it also interacts with a whole complex set of intermediaries between the electricity producers, gas producers, and renewable energy producers. You might have district heating systems, for example, where waste heat from generation processes or from combustion of waste products is produced around a network that can go both into transport and industry. You have industrial processes that produce waste heat that could be used in buildings. Increasingly, for example, heat pumps are used in buildings for heating. They can produce surplus energy, just as a PV system can produce surplus electricity. A heat pump can produce surplus heat, and that can be distributed to others, to other buildings, to other users. Then you've got a whole range of things around synthetic fuel production, hydrogen production that might exist in a system, and you've got electric vehicles. And your electric vehicle, for example, might get charged during the day in one location, come back to the home, and is actually a source of electricity from its own batteries. So you've got a complex interaction of systems that come into buildings. So buildings don't exist in isolation. They exist as part of a complex energy system, and that's all we need to be taken into account as one designs buildings in future. Another very important issue is indoor air quality. And as I said earlier, one of the strategies to reduce energy use in buildings is to reduce the air change rate in buildings. In other words, you've either heated or cooled the air that goes into a space, depending on whether there's a heating or cooling load, and rather than having to continue to heat and cool that building, reduce the amount of air exchange going through the building. And that's a sensible strategy from one perspective. However, if you don't have sufficient airflow in the building, there's a whole range of issues to do with contamination, to do with buildup of moisture, to do with buildup of bacteria, viruses, mold, etc. So there's a huge impact on health, and this is particularly relevant in the current global pandemic, where one of the strategies adopted in many countries to try and reduce the prevalence of COVID is to increase the air change rate in buildings so that virus-borne air is removed from the space and is diluted. So from an energy saving perspective, one wants to reduce the air change rate, but from a health perspective, one wants to increase the air change rate. So all this means that that strategies for buildings need to have two things. Either you are, if you're looking at providing warm air to a building, you're preheating that air, perhaps through glazed additions to the building, perhaps through air heated solar collectors. So that you're preheating that air to reduce the energy consumption in heating the air. If you're cooling that air, likewise, there may be shaded panels, for example, which are producing cooling, or more mechanical cooling systems, etc., to cool the air coming in, and also recovering heat from the airstream that leaves the building. That heat, by the way, could then be used if you're in a cooling application for drying the desiccants in desiccant cooling systems, for example. But increasingly, a challenge in buildings from an energy efficiency perspective is how to balance indoor air quality from an occupant perspective and energy perspective. This also comes to a fundamental point in that buildings are not energy systems. The function of a building is to provide a comfortable and healthy environment for the occupants, and the use of energy is incidental to achieving that goal. So the first thing is, it's always important to look for the occupants' needs first, and then see how those needs are best met from an energy efficient perspective, rather than designing the building to be energy efficient without considering the occupants. And that is actually a critically important part of design, that the air quality issues come in. The next one I'd bring in is an area of which might surprise you, which is daylight. And daylight in buildings is taken for granted, but is very important. It comes back to this idea of the human design of buildings. And one might think, for example, that a very energy efficient building would be one which had a solid fabric, minimum glazed apertures to avoid the heat losses from those apertures, or indeed excessive solar heat gain that overheats the building, and artificial lighting. That would not be a good idea. And that's because daylight provides more functions than perhaps one would realize. There's obviously the visual system, the idea that the reflection of daylight on the walls of the environment, etc., provides sufficient light for visual tasks. Okay, but more interesting than that is that the circadian system, the time clocks in our bodies are actually set by daylight, and they're set by a part of the eye that responds to a different part of the spectrum from the visual system. So it's a non-visual response, but it's a non-visual response in the eye. Okay, and the cells that do that in the eye were only discovered in the past 15-20 years. Okay, that the operation of the human circadian clock is determined by non-visual effects received at the eye. So, and the interesting thing is that part of the spectrum is in daylight, but actually is not in most artificial lights. So being continually under artificial lights actually is a major problem in maintaining the circadian rhythm, the body clock, and that is a particular issue in children, in elderly people, in people who are ill, and if it's not maintained properly, can lead to serious illness, or can accentuate serious illness. It can lead to depression and a whole range of other areas. Also, daylight is important for vitamin D synthesis, for bone health, for the immune system. It's important for the development of the human eye in children. So particularly if children are not exposed to daylight on a regular basis, they end up with myopia, short-sightedness. So there's a whole range of reasons why you need daylight in buildings, and the particular characteristics of the spectrum of daylight enable these to be achieved. Artificial lights. The spectrum for artificial lights is primarily to do with the visual system and doesn't provide all these other benefits. Interestingly enough, this can be a challenge in countries which are sunny. For example, Singapore, there is a very high incidence of myopia, short-sightedness, and that is because children, because it's a very hot country, very, very hot, they're in air-conditioned shopping centres, air-conditioned apartments, and move from enclosed artificially lit environments to other enclosed artificially lit environments and don't see sufficient sun. So ironically, the avoidance of outdoor conditions in some very sunny climates could lead to issues with deprivation of daylight. So designing buildings for daylight is important. That means one needs lots of windows. It means those windows have then got to be designed to avoid overheating, avoiding glare, etc. Now, none of this is new. I've got a little advertisement here for healing daylight for the 1920s. School building designs where in Europe, where buildings were designed to have lots of daylight for both visual things and for the UV light, providing disinfection, for example. And there are systems, as are shown here, for projecting daylight deeper into buildings, so that particularly at when the sun angles are not correct to get the daylight in, one's deflecting it into the building. So daylight design, again, is an important thing from a point of view of occupancy. Okay. So far, I've talked about operational energy use, how buildings use energy when they are occupied by people over their operational life. But in fact, the energy use in buildings arises from much more than just the energy used to keep a building heated, cooled, lit, provide hot water, etc. There's a whole lot of energy used in the construction of the building, from the extraction of the materials in the ground, their transport to the site, their manufacturing to building components, the actual construction stage of the building, again, more transport, the conversion process at site. Then the use stage, which I've discussed to date. But then at the end of the building, there's demolition, there's removal of those demolished components, there's the disposal of those. So there's a whole set of processes around building which also use energy, and there's carbon emissions from all those processes. So it's not just a matter of looking at the actual operation of a building from an energy perspective, but looking at the whole life cycle of the building. And that leads us into the idea of life cycle emissions and the energy use in building materials. And here, in the sort of pink color, you can see the operating energy of a building with time. And an initial yellow there, which is the materials and energy used in its construction. And there's significant energy involved in construction. That's the first thing to say. And your total greenhouse gas emissions are the greenhouse gas emissions for the building's operation, the embodied greenhouse gas emissions in the building materials, and those produced during construction, renovation, etc. And this comes into material selection, and this pyramid is a pyramid of the embodied carbon dioxide per cubic meter of a range of materials. This is actually an example produced in Denmark, with the use of wood being at the bottom, because wood, while it's used in the building, those trees have been absorbing CO2, and that CO2 is locked into those trees as wood while it's used in the building. Then you look at the top there of cement and steel, and newly produced cement and steel has huge high temperature processes associated with it, and high embodied energy, high embodied carbon dioxide in it. Now, that can be avoided if one uses recycled steel, for example, so that and it's not subject to further high temperature processes. So there are choices in terms of, but there's a hierarchy of materials, and if one wants to reduce embodied energy, using materials at the bottom of this pyramid would be preferable. This can be done in a number of ways. It can be done by regulation, and actually, there's a whole thing around regulating the embodied energy of materials, what materials can be used. It can be used by designers in terms of component selection, what materials they choose to use, how much wood, how much steel, how much cement they use in construction, for example. And it can also come into design choices, and it's possible to get very similar building performance with different components that have very different embodied energy. If I can give you an example, if you look at, for example, advanced glazing systems, advanced windows in buildings, you would see buildings, for example, with triple glazing to reduce heat loss, would have the same performance as buildings that would use vacuum glazing, which is 2 sheets of glass with a vacuum between them. The 2 sheets of glass, the vacuum cleaner between them have 2 sheets of glass. Triple glazing has 3 sheets of glass. They have identical performance in terms of overall heat loss, but the vacuum glazing has a third less glass and a third less embodied energy. So there are design choices as well that come into these kind of things. Okay, this is important in terms of the renovation of buildings, because when you renovate a building, you are introducing energy in the renovation process, in the new materials you've introduced, in the better components. So it's not just new buildings. When buildings are renovated, there's an increase in emissions, and that increase in emission has a payback period until the reduction in operational energy has offset the additional emissions created by the materials in renovation. So we've got declarations that came out of the Paris Accord, recently reaffirmed in the meeting in Glasgow, to substantially reduce emissions by 2030. To do that, if you're refurbishing buildings, this is the business as usual line, is the red line there. Deep renovation is that green line. It's important that the new emissions created by the materials associated with the renovation process itself are minimized, so that period of payback is small. Okay, one issue I just want to touch on before drawing to a close and inviting questions is all of this has financial implications, and particularly for existing buildings, how this is paid for is very critical. There's someone in the background with a microphone on, if they could mute, because just if they would please. So the finance of remuneration is important, and this comes down to fundamentally an issue of what does the state pay for and what do individuals pay for. There's a public good in reducing CO2 emissions, which is part of national policy, and there's a private good to individuals of the energy savings that come and the benefit to them in energy savings. And financing needs to take account of that, and there are various mechanisms that exist and are growing to do that, and I won't go into detail. Some are listed here. One challenge, and the reason why there's an elephant there, is there's a saying where I am of the idea of an elephant in the room. In other words, something in the room that you don't discuss too much. All right, and the issue here is fuel poverty, and that if people are spending more than 10% of their income on energy, there's an idea of fuel or energy poverty, and those people do not have the ability to afford to renovate their building and need government intervention. Okay, to conclude, and then I'll invite questions. There are multiple different factors for energy buildings, and they're summarized in this figure. There are many benefits that accrue, but they accrue to very different stakeholders, as you can see, and important that we take those things into account. There's no single silver bullet. There's no single way to decarbonize buildings, and it needs legislation, it needs design work, it needs new technologies. Key is phasing out fossil fuels, reduce the energy needs of buildings, and reduce the embodied greenhouse gas emission in building materials, components, and processes. All of this, by the way, actually creates jobs and modernizes ways of working. And there also is a whole range of interventions by government that promote investments and use grants and incentives. I'll conclude there. Thank you very much indeed. There are two reports I'd advise if people are interested in this more. I chaired a group for the European Academy Science Advisory Committee called Decarbonisation of Buildings for Climate, Health and Jobs. And that report is available at easac.eu, and is a very comprehensive report on this topic. There's a paper just published in the Proceedings of the Institute of Civil Engineers in the UK called Decarbonising Buildings in Europe, a briefing paper, and that's available in the most recent issue there, and also covers these topics as well. I will stop there and happy to answer questions. Thank you very much indeed. And hopefully, if I can stop sharing a screen here, I'll be able to answer questions. Let me see if I can stop sharing. There we go. Okay. I'm happy to answer any questions at all. Thank you very much indeed.
Sir, the question is from the other area. It is not related to the topic actually. As you are the one of the top solar engineer in the world. So I would like to ask, what are the recent trends in solar energy in which we can do research?
Okay. Yeah. Okay. Thank you. There are actually many. I mean, there are many fields. There's probably several hours of discussion as to the fields of solar energy. But I think fundamentally, if you the issues, there are a lot of issues to do with photovoltaic systems and how energy is stored within photovoltaic systems, and how performance can be improved. There's a microphone in the background. If you could just turn the microphone off, please. No, okay. So there's a lot of potential research around photovoltaic system performance and how, for example, photovoltaics get warm when they're in the sun. That reduces their efficiency, etc. So looking at heat transfer in photovoltaics, a lot of work is done on the electrical performance of photovoltaics, but less on the thermal. So I think that's an important area. I think there are a huge amount of work on designing new building materials that harness solar energy and how they integrate into the facade. I think a considerable amount of work on a whole range of applications, for example, new collectors for industrial process heat. I think that's going to become increasingly important, particularly around things like air heating collectors. New systems for concentrated solar energy. In my own work, for example, you can use luminescence to concentrate diffuse light. The limits of optical concentration, it's very difficult to concentrate from a diffuse sky, and using luminescence to concentrate diffuse light, and that takes into a whole range of other applications in that area, and also the applications of new materials. So new absorber materials, which have different characteristics, new materials, which might have switchable properties, go from transparent to opaque to allow better control of systems. So there are many areas of research in solar energy, and perhaps another lecture, another time, I could just talk about research frontiers. But it's certainly an exciting topic to be involved in, and because there is now actually internationally an industry around that. There's also a take-up of the ideas, and there are lots of people looking for new ideas in the solar energy space. And I should say a big thing is actually just in the idea of autonomous devices that use solar energy, and increasingly you're seeing, obviously for many years now, you've seen the pocket calculator is solar powered, but increasingly seeing a lot more things that are autonomously powered by solar energy, and how to integrate solar energy into systems, so that you're not looking at something to which solar energy is added, but the solar energy is intrinsic. I think that is also an important area of research.
Thank you, sir, for your valuable suggestion. And there is one more question in chat box. That is, how far can we push smart building operation and performance?
It's actually largely an economic question. It's possible in most climates to design buildings that have little to no energy use. Okay, it is technically possible to do that. Okay, but the challenge is how to achieve that goal economically. So it's to do with factors to do with the design process, with products that are of low cost, to do with construction processes that have use modular components, prefabricated components, and are operationally efficient. Okay, so at a technical level, it's possible to get down to net zero energy buildings. The challenges are really to make the products and processes that achieve that economically viable.
Sir, there is one more question in chat box. How can we minimize the heat transfer through glass and windows of a room because effect of convection and radiation, which is coming from atmosphere and sun?
Yeah. There are a variety of techniques. Okay, essentially they range from having multiple panes of glass, so that if you've got, say, 3 panes of glass, one traps air layers between the glass, and air is a very good insulant as long as it doesn't move. If you trap air is a very good insulation material. So trapping insulation between the glass panes is one approach, and you have triple glaze systems. Another approach is to have things called aerogels, which are essentially a foam, lots of bubbles, okay, and that traps the air within a tight cellular bubble structure that's retraced between 2 sheets of glass. So using aerogels. And another technique which I've done quite a bit of work on is the idea of removing the air altogether and having a vacuum between 2 sheets of glass. Now, if you have vacuum 2 sheets of glass, then obviously you've removed the convective heat transfer, but then the radiative heat transfer dominates, and radiative heat transfer is T to the 4, so it gets quite significant. So if you're having vacuum glazing, one needs to have low emittance coatings to reduce the radiative heat transfer in the system. And there are a number of now manufacturers of vacuum glazing systems as well. So essentially 3 approaches: multiple panes of glass, intervention of things like aerogels to reduce the convective heat transfer between the glass, or vacuum glazing would be the 3 key approaches on that.
Thank you, sir. And sir, there's one more question. May you please brief me about the cogeneration plant in which solar photovoltaic and solar thermal are collectively producing power and electricity and heat?
Yeah.
In Europe.
Yeah. It's a very it's a very interesting area in that solar energy producing electricity works obviously very well during with climates with high direct thermal incidence, in other words, very sunny climates during the day. But the question is, what happens at night? Okay, and there's a number of answers to that question. If the energy system has a low load at night, in other words, everyone's asleep, then actually what happens at night doesn't matter. All right, because other parts of the energy system would provide it. Okay, if one's seeking, though, to have high renewable energy contributions, and there is a significant energy load at night, then it has to be met either by energy storage. So you store the energy from the solar energy during the day at a high temperature using molten sodium, and use it at night, or you generate from something else. Okay, and in Europe there's one plant in a place called Lleida in Spain, where you have cogeneration using solar energy during when it's sunny, essentially, but when it's not sunny or at night, you need to produce. There's the use of biomass. Okay, and the biomass is used because then rather than have an auxiliary heating source, the biomass has inherent energy storage. Essentially, it's renewable energy that can be dispatched whenever you wish. Okay, whereas if you used wind energy, for example, it's only available if there's wind. So the idea there is to use to have the same plant, the same turbines, the same energy generating kit, but that it uses the heat generated from the sun when that's available. When that's not available and there's a demand from the grid, there's a biomass combustion as well, and the two are linked together. And that plant is operated very successfully in Lleida, which is quite far to the north of Spain, and extends the range by which you can use concentrated solar for power production.
Participants, any other question you want to ask? You're most welcome to ask any question.
Absorbed and how many percent reflect by solar panels, and reflected energy can further be used to generate electricity by any method.
Could you repeat the question? Sorry, there's a lot of echo there. Apologies.
Please repeat your question.
How many percent of solar energy absorbed and how many percent reflect by solar panel, and reflected energy can further be used to generate electricity by any other method like total internal reflection or reflection?
Okay. Yeah, there are. Yeah, you could devise systems called PV thermal systems, where essentially one has a photovoltaic panel, okay, and produce electricity, but when a panel gets hotter, the electrical efficiency goes down. It goes down by about 0.5 of a percent for every degree Celsius temperature rise. Okay, so to prevent that, you can actually then move a fluid either by having copper tubes connected to the PV panel, or airflow through the system to cool the PV and produce heat. So effectively, you can design systems that can do both. And how much of each you actually do depends on the economic value of the PV electricity and the heat in the application context. It's not really a technical question. One could design systems that produce a small amount of PV and a lot of heat, or conversely, a large amount of PV and a small amount of heat. Okay, but which you do really depends on the load demand profile, what the demand for heat is, and what the demand for electricity is in that application. So one can literally sort of almost size the system to meet those particular loads in a given climate. More interestingly, there are a variety of systems where you split the solar energy, what's called beam splitting, and in beam splitting, you can also do that in a spectrally selective manner. So some part of the spectrum can go to one device, another part of the spectrum go to another device, so that you can beam split to send some of the spectrum with the particular ways that it's absorbed by a particular PV cell very efficiently, okay, and the rest of the spectrum to a solar thermal device, okay. Solar thermal devices are not usually very spectrally selective. They integrate the spectrum they receive, okay, but nevertheless, that's another technique of actual beam splitting as well. So there's a variety of techniques that can be used, but in terms of the mix of PV and thermal output, that can be varied by design. It's a design choice. And the design choice really depends on the characteristics of the intended application, and designing a system for that.
Thank you, sir. Thank you so much, sir, for your valuable suggestion and the keynote lecture. Your eminence presence has added value to this conference, and it is our honor and privilege that it is the first international conference in our institute, and you are gracing the function with your eminence presence. It can't be more bigger than this. So I would like to thank you, and sir, and if possible, we will definitely try to hear you again after in future also.
Yeah, it's a pleasure to speak, and I look forward perhaps in a future time to be able to visit you in person. So I look forward to that.
Thank you so much, sir, for your lecture.
Thank you.
So,
Thank you, sir. Now we are having the presentation for the participants. In that, there is session chairs Dr. M.K. Gaur and Dr. Anil Singh Yadav will be the session chair for this technical sessions.
Good afternoon. I am present.
Sir, 1 minute.
Sir, Anil sir, very good afternoon, sir.
Sir, good afternoon. Sir, there is some problem in my video. It is not
Yeah.
visible. I am trying to.
Yeah, no problem.
Dear participants, for this session, the technical session, we have 3 session chair, and the first one is Professor Amit Pal from the Delhi Technological University. Professor Amit Pal is there.
Yeah, welcome all.
Thank you, sir. And another one is Professor M.K. Gaur. And the third one is.
Sir, good afternoon. Good afternoon to everybody.
Yes, sir.
Sir, good afternoon, sir.
Good afternoon, sir. Good afternoon. Good afternoon to everyone, sir.
Anil sir, good afternoon, sir.
Very good afternoon, sir.
Anil sir,
Sir, good
very
afternoon.
good afternoon, sir.
So, our first session chair, Professor Amit Pal, is currently working as professor at the Department of Mechanical Engineering, Delhi Technological University. That was formerly Delhi College of Engineering. Sir obtained his BE Mechanical from Bikram University, Ujjain, and Master of Engineering from University of Mumbai and PhD from Faculty of Technology, University of Delhi. Sir has more than 23 years of experience in teaching and research with major research interested areas, including IC engine, biofuels, pest management, pollution mitigation, etc. And Sir has published over 50 research papers in respected international journals and conferences. Professor Amit Pal received Commendable Research Award 2019 for the paper Experimental Studies of Utilization of Prunus Armenia L. Wild Apricot Biodiesel as an alternative fuel for CI engine in waste and biomass vaporization. And first prize of the research paper, Recent Developments in Biodiesel, Part 1, Biodiesel Production Technology, and second prize for the research paper titled Optimization of Solar Assisted Production of Biodiesel from Cotton Seed Oil. Sir has been expert member in various committees of CPCB India, DTC Delhi, GGSIPU, NIOS, and NPOS India. Professor Amit Pal authored, edited 5 books on renewable energy, Recent Advance in Mechanical Engineering, Springel LNME 2020, WinTech Proceedings in Energy, Heat and Mass Transfer. And Sir also wrote chapter in Advances in Alternate and Renewable Energy Technologies with ISPN. Professor Amit Pal was the investigator from different research projects sponsored by the government of Delhi, Arihant Energy Solution and DTU, costing over 17 lakh Indian rupees. He is a lifetime member of Indian Society of Mechanical Engineering, the Indian Society of Technical Education, the Solar Energy Society of India, and the Ultrasonic Society of India. Professor Amit Pal organized many workshops, conferences, faculty development program, and also delivered over 30 expert lectures in many reputed conferences, FDP seminars, etc. Sir has also actively participated and organized in over 25 short-term courses, QIP programs, and FTP programs organized at DTU and other reputed organizations. And personally, I feel privileged to be his student in the MTech. And under his supervision, I was awarded the highest marks in the project. And sir, it's my, I cannot I'm feeling.
Your hard work.
And our second, thank you sir for coming. Our second session chair is Professor M.K. Gaur. Professor M.K. Gaur has obtained his BE from Oriental Institute of Technology, Bhopal, and Master of Technology in Engineering Materials from MANIT Bhopal, and PhD from the MANIT Bhopal. Sir has been working as a professor and head in mechanical engineering, associate proctor, and in charge of the institute I apologize for that was network issue.
It is not audible. Some voice-
Am I audible?
Yeah, now it is audible.
Thank you, sir. Professor M.K. Gaur has been working as professor in and head in mechanical engineering, associate proctor, and in charge of Institute Industry Interaction Cell at MIT's Gwalior. And sir has more than 18 years of teaching experience of postgraduate and undergraduate classes. Sir has authored 2 book titles, Solar Energy, Problem Solutions and Experiment, and Optimization of Machining Parameters of Hard Porcelain on CNC Machine. 95 of his papers have been published in various reputed international and national journals and conferences. Sir has attended many technical courses and 1 week summer school in UKERC at University of Sussex, Brighton, UK in July 2009. Sir has worked in the broad area of thermodynamics, heat transfer, solar energy, solar distillation. He is life member of IET, and faculty advisor of Society of Automotive Engineers. Welcome, sir. And
Thank you.
our-
Thank you.
And our third session chair is Professor Dr. Anil Singh Yadav. He has pursued his BE from MIT's Gwalior and further earned his MTech and PhD from MA NIT Bhopal. And sir is presently working as a professor at LNCT Bhopal, and prior to his, he has served as various institutes. Sir has an excellent teaching experience of more than 24 years and published more than 100 research papers in his name and published 6 books. And his research interest being CFD, fluid mechanics, heat transfer, turbulence, and solar energy. So personally, sir, I am very honored that you have reviewed so many papers in this conference. Welcome, sir.
Thank you.
So, sir, should we proceed for the presentation?
Yes,
Yes, yes, you can start.
Paper ID 4.
Sir,
Yes, please share your presentation and start.
okay. Sir, it is not shareable.
Just a minute. Now you can share.
Okay, sir.